Hello students, welcome to the physics class on mechanics, which comes in your paper 1 of your semester 1. We are dealing in unit 2. I am Chandana, assistant professor of physics from Government Degree College, Khartaba. So let us have a quick recap on the previous classes, what we have told. See, I have done with center of mass, laboratory and center of mass frame of references, and conservation of linear and angular momenta. Where we have done center of mass. What is center of mass? For any system of particles, which we take a random number of particles, if I have n particles, 1, m1, m2, m3, m4, m5, m6, so on, so on, mn particles. So if n particles in my system, then the entire mass is said to be concentrated, and the entire system's mass is said to be concentrated at one singular point, one single point. What is that single point called? Center of mass of the system. Center of mass of the system. So we used some coordinate system, and we have done the position vector, and we have derived the various parameters of center of mass, like momentum, velocity, and acceleration also we have done. This comes under center of mass of the system. Now we have laboratory frame of reference and center of mass frame of reference. Here, laboratory frame of reference, we have an ideal point which appears to be the center of the system. We consider a frame of reference at that particular point, origin. But here, when I consider the origin to be the center of mass of the system, the origin of my frame is always the center of mass of the system. Then such type of frame of reference is said to be center of mass frame of reference. Okay. Then we have done conservation of linear momentum and conservation of angular momentum. That means conservation of linear momentum, where I have, what do I have? Conservation of linear momentum. We know that linear momentum P is equal to mv. So I want this to be conserved. That means initial momentum is equal to final momentum. So how do I get this? Whenever I have external force acting on the system equal to 0, that is dp by dt equal to 0, then what happens? My momentum is constant. That means P remains constant. That means m1 v1 equal to m2 v2. That means my initial momentum will be equal to the final momentum. That means my momentum is conserved. That is linear momentum. Similarly, for angular momentum to be conserved, what will I take, students? Tau bar, that is equal to dl by dt. What is L here? Tau is torque, L is angular momentum, that is r cross p. So what I'll get here? I want dl by, I want my angular momentum to be conserved. That means L to be constant. That means what should be equal to 0? The external torque applied on the system. If the external torque applied on the system is 0, in rotational dynamics, we take that the angular momentum is conserved or constant. The angular momentum is constant. Okay. So all these three things we have learned in our previous class. So I am just teaching each and every topic in step by step, so that we'll have a clear understanding. And you write down what all the points I teach you in this whiteboard, because it would be as your running notes or reference notes. In the live class, you'll write the running notes. No, similarly, you have to watch my video, and along with that video, you have to write down on your notes, so that there won't be any problem. Later, when you have doubts, you can directly ask me through WhatsApp, or else you can call me right back. Then we have summary. Then we'll see the summary after I teach in your whiteboard. Okay, let me share your whiteboard now. Now, today we will just deal with some new topics. Work energy theorem. See here, work energy theorem. Okay, so this is something. See here, you're observing the terms work and you're observing the term energy. So this theorem relates the work and energy. So it is clear now for you all. So this theorem is relating between work and energy. So what does this theorem state is? The work done by a force, the work done by a force on a particle is equal to the change in kinetic energy of the particle. the work done by a force on a particle is equal to the change in kinetic energy of the particle. The work done by a force on a particle is equal to change in kinetic energy of the particle. That's what we have to talk about. That is the theorem which states the link between work and energy. So let us know this. See, you all know that what is the work done? Force into perpendicular distance. If I have dr, the distance, f dot dr will be f dr cos theta, where theta is the angle between the force and the displacement vector dr, right? Where dr is the displacement vector, I can take, and I take f is the force acting on the particle. Now, what is the angle between f and dr? Ma? It is theta. Then I get f dot dr is equal to work done is equal to f dr cos theta. Okay, but you know that because of small displacement, I take it as f dr cos theta dr. Small displacement, that means dw. So I want w. What I'll do? Integral f dot dr. Right? Integral f dot dr. That is equal to integral f dr cos theta. So I substitute dot product here, that is f dot dr equal to f dr cos theta. Okay, so I can write it as integral f cos theta into dr. So let me take it as equation 1. Okay, so I have work done on a particle, work done on a particle by a force f. Okay, is given by integral f cos theta into dr. Okay, students. Now let me relate this work to kinetic energy, that is change in kinetic energy of the system, right? Okay, now consider that a body of mass, let me take it, let me write and tell you so that you will be able to understand easily. This is nothing but w. Now consider body of mass m is acted upon by a force f along x-axis. So if I take along x-axis, if I take the force is acting on a mass m by f force along x-axis. What's happening? Suppose the body moves from positions x1 to x2. Okay. Now because of this force, what is happening? This body is initially at x1. It got displaced to position x2. Okay. Okay. Now let us think that the velocity of the body is from initial state, that is v1, it got increased to v2. So now the work done by the force in displacing this, it will be how much more? x1 to x2 f dot dx, f1 to f2 f dot dx or f dx, force into displacement, right? F into dx. Now let me give it as equation 2. Now we know that from Newton's second law, what do we know? F is equal to ma, that is equal to m dv by dt, or m d square x by dt square, right? M d square x by dt square, or in other way I can write it as m dv by dx into dx by dt, right students? So here I'll have dx gets cancelled and I'll get dv by dt. So I can write either this way, f is equal to ma, or this way, because rate of change of velocity is acceleration, rate of change of displacement is velocity. So double derivative of displacement gives you acceleration. So m into dv by dx into dx by dt. Okay, so I'll get, finally I can write it as m dv by dx into dx by dt. So what is mv into dv by dx? I can write this as mv, because dx by dt is v. So mv into dv by dx. So mv into dv by dx. What is mv into dv by dx, students? mv into dv by dx is nothing but my force according to Newton's second law. Okay, so I'll write here f is equal to mv dv by dx. Okay, students. So now I'll substitute this f in this second equation. What I'll get? W is equal to integral x1 to x2, what is f? mv dv by dx into dx. Okay, so what I'll get, that is equal to m into, at x1 what is the velocity? v1. At x2 what is the velocity? v2. So I can change it as x dx cancelled. So what I'll get here, I will write directly here. So what I'll get, m into integral v1 to v2 v dv. Okay, so v dv. So what is integral v dv? It is nothing but m into v square by 2 from v1 to v2. So I'll get m into v2 square minus v1 square by 2. Right? That is my work done. So what is half m v2 square minus half m v1 square? What is this, students? This is nothing but kinetic energy after applying force. That is half mv square. And kinetic energy before applying force, initial kinetic energy. So what would be this? Change in kinetic energy. Change in kinetic energy. So the work done by a force F on a particle of mass m is equal to the change in kinetic energy of the particle. Change in kinetic energy of the particle. Okay. So finally I got that the work done on the particle by a force equal to change in kinetic energy of the particle. So this is called work energy theorem, which relates the work done on the system and the change in the kinetic energy of the system. This is called work energy theorem. Okay, students. So let me just revise you once. What did I take? First, I have taken a mass m, which is acted by a force F, which is displacing from this to here. Because of this force, it's traveling 4 positions. At first, it is at x1 and then now it is at x2. At first, the velocity is v1 and then it is v2. Now we know that the work done is equal to integral f dot dr or f dr. Integral x1 to x2 here, f, I'll get here f dx. So what is f according to Newton's second law? F is equal to dp by dt. That is m dv by dt. That is equal to m into d square x by dt square, or m into dv by dx into dx by dt. Right, students? So that my dx will get cancelled and I'll remain with m dv by dt. Right? So what is dx by dt? Change of rate of change of displacement. That is velocity. So mv dv by dx. That is my f. So now I substitute f in work. That is x1 to x2 mv dv by dx into dx. So dx gets cancelled out. So I'm remained with x1 to x2 v dv. So when I'm talking about integration about velocity, I'll change my limits to v1 to v2. So what I'll get, m into v square by 2 from v1 to v2. So m into v2 square minus v1 square by 2 is nothing but half into m v2 square minus half m v1 square. That is change in kinetic energy. Okay, students. So this is work is related to kinetic change in kinetic energy. This is the work energy theorem. Okay. Now let us go for collisions, which is very important concept. Okay. Collisions. You have learned in your intermediate collisions. Collision means what? What, students? You question yourself. What is collision? It is nothing but redistribution of momentum. Redistribution of momentum. It is nothing but redistribution of momentum of the bodies. Okay. If you take two bodies, let me take that their initial velocity is u1, one initial velocity is u2 for this body. Now if they are coming close to each other, they will collide with each other, right? After collision, they will have velocities v1 and v2 if I take. These are the final velocity of the body m1. This is the final velocity of the body m2. What is happening? There is a distribution of momentum among these two bodies or two particles, okay, which are approaching to each other. Okay, based on this distribution of momentum, so there are two types of collisions we have. What are the two types? One is elastic collision, the other is inelastic collision. Okay, so one is elastic collision, another one is inelastic collision. So what is elastic collision, students? When the kinetic energy and the momentum of the particles remain conserved. Kinetic energy and momentum, if both are conserved in a system, then the type of system is said to be having, that type of collision is said to be elastic collision. If in a system the kinetic energy and momentum both are conserved, then the system is said to be elastic collision. Okay, for example, atomic and nuclear collisions. Atomic and nuclear collisions can be treated as elastic collisions, for example. So what is an elastic collision? When the kinetic energy and momentum of bodies or particles remain conserved in the collision, then such type of collision is said to be what? No, elastic collision. That means if I consider this system only, then what happens? First one is kinetic energy momentum conservation, m1u1 plus m2u2. This is the initial momentum of the system equal to m1v1 plus m2v2. Final momentum of the system, initial, final. So this is conservation of momentum. I want conservation of kinetic energy. So I'll get half m1 u1 square plus half m2 u2 square. This is initial kinetic energy equal to half m1 v1 square plus half m2 v2 square. So this is final kinetic energy conservation. So the kinetic energy is also conserved. Initial equal to final, initial equal to. If these two conditions are satisfied, then such type of collision is said to be elastic collision. Okay. Now let me go for one second. We go for inelastic collision. Inelastic, which is not elastic. It's called inelastic collision. So what is inelastic collision? You all know that. That only momentum is conserved here. Only momentum is conserved. Okay, but there is no conservation of energy, kinetic energy. Such type of system is said to be having an elastic collision. See, perfect example you have learned in your intermediate is when a bullet is targeted to a wooden block, then the bullet gets embedded into it. Right, the bullet remains inside this wooden block. So now this can be treated as an elastic collision because here the kinetic energy is not conserved, but only momentum is conserved. Momentum is conserved. Okay, so let me give you here that equations. So you know momentum is conserved means again m1u1 plus m2u2 equal to m1v1 plus m2v2. But kinetic energy, while I'm writing that half m1u1 square plus half m2u2 square equal to half m1v1 square plus half m2v2 square plus some energy. Either this is a negative value or a positive value based on the system. We get this value, but see, it is not equal here. There is some additional term here to this final energy. So this is called non-conservation of kinetic energy. That is hence the system is said to be having inelastic collision. Okay. So this is called inelastic collision. Okay, ma. For elastic collision, we have conservation of momentum and kinetic energy. But for inelastic collision, we have only momentum conservation, but there is no kinetic energy conservation. Okay, students. So this is the major difference between inelastic and elastic collision. Okay, you already learned the coefficient of restitution also in your intermediate. Okay, you just revise that and come. Even this is also important, but here in our degree syllabus you directly go into elastic collision in 2 dimensions as the next topic, then impact parameter, then in 3-dimensional elastic collision. Okay, so let me go to that. That is in elastic collision you have learned now. So let us go for uh, elastic collision in 2 dimensions. Okay, so let me derive that equations. So elastic collision in 2 dimensions. Okay, so what is elastic collision in 2 dimensions? Let us see. You know, we have center of mass uh, reference frame. I already told you. We have to consider that frame now. Now let me talk about center of mass frame of reference. Before that, let me consider 2 bodies. Okay, which are of masses m1 and m2 as I drawn before. u1 by and u2 are the initial velocities of the body. Okay, now according to laboratory frame of reference, what I have is u2 is 0. If I consider this case that u2 is rest, m2 is at rest, and m1 is coming and it is colliding with m2, then what happens? uh, I have conservation of momentum m1 u1 because it is an elastic collision. I can write down m2 into u2 equal to, the center of mass frame of reference m1 plus m2 into vcm. This is velocity of center of mass. Okay, this would be equal to this one, as I told you when I'm teaching you center of mass. Okay, now total momentum of the system will be equal to the entire masses combination into the velocity of the center of mass gives you the total momentum of the system. Okay, so what happens now? What is my velocity of center of mass? m1 u1 plus m2 u2 by m1 plus m2. So this is my velocity of center of mass. Okay, if the velocity with which the center of mass is moving with respect to the laboratory frame of reference is vcm. Okay, students, vcm. Now let me take that u1 dash and u2 dash are the initial velocities of the two particles in my center of mass frame of reference, and v1 dash and v2 dash are my final velocities of the bodies in my center of mass frame of reference. Okay, but vcm is the relative velocity between the laboratory frame of reference and my center of mass frame of reference, while u1 dash and u2 dash are the velocities of the two bodies with respect to laboratory frame, center of mass frame of reference, and these are all final velocities with respect to the center of mass frame of reference. Okay, that's the reason I have told you what is center of mass frame of reference and laboratory frame of reference. You have to understand that. Okay, now let me write that equations. So what happens now? You tell me, students. So u1 dash will be u1 minus vcm. Okay, similarly u2 dash will be u2 minus vcm. Why? Because VCM is the relative velocity between the laboratory frame of reference and our center of mass frame of reference. So that is the relative velocity. So VCM is equal to U1 minus U1 dash. That means U1 dash is equal to U1 minus VCM. Similarly, U2 dash is equal to U2 minus VCM. Okay. So what happens since U2 is equal to 0, because U2 is rest, I have told you. So U2 dash equal to minus VCM. U2 dash equal to minus VCM and U1 dash equal to U1 minus VCM. Okay, similarly, I'll take V1 dash, final velocities of my bodies in my center of mass frame of reference. What I'll get? V1 minus VCM, and V2 dash I'll get as V2 minus VCM. Okay, so V1 dash equal to V1 minus VCM, V2 dash equal to V2 minus VCM. Here V1 and V2 are present. Here V2 is not 0, students, because after collision, now the mass M2 will move with some velocity, right? That is V2. Before collision, it is V2 equal to 0, but after collision, V2 won't be equal to 0. So V2 dash equal to V2 minus VCM. Okay, here V1 and V2 are what I have already told you. They are the velocities of final velocities of the bodies in after collision in laboratory frame of reference. But V1 dash and V2 dash are in center of mass frame of reference. Okay, so U1, U2, V1 and V2 are in laboratory frame of reference (LFM). Here in center of mass frame of reference (SMF), CMF, we have U1 dash, U2 dash, V1 dash, and V2 dash. Okay, now based on the conservation of linear momentum, because it is an elastic collision, we have both kinetic energy and momentum are conserved. Momentum are conserved. Okay, so what I'll do here, so both kinetic energy and momentum are conserved. So let us take this. When m dash plus m2 u2 dash equal to 0. Similarly, m1 v1 dash plus m2 v2 dash equal to 0. Okay, because in center of mass frame difference, what do we know? The center of mass is always at rest. So what should be happening now? M1 u1 dash plus m2 u2 dash should be equal to 0. And also m1 v1 dash plus m2 v2 dash equal to 0. Because in center of mass here, what should be m1 plus m2 into UCM. This is 0 because the center of mass frame is always at rest. Here also VCM, that is equal to 0. So m1 u1 dash plus m2 u2 dash equal to 0 and m1 v1 dash plus m2 v2 dash equal to 0. Now what I'll get from the above first equation, m1 by m2 equal to minus u2 dash by u1 dash. Right, from this equation, I'll get this. M1 by M2 I divide by M2 on both sides in this equation, then what I'll get? To minus U2 dash by U1 dash. Right? Similarly, from this equation, what I'll get? M2 by M1 equal to minus M1 V1 dash V1 dash, right? V1 dash by V2 dash. This is M2 by M1. Here what happens if I take M2 by M1 minus U1 dash by U2 dash. M2 by M1, M2 by M1 we have. So equating these two equations, what I have, minus U2 dash by U1 dash equal to minus V2 dash by V1 dash. Okay students, minus U2 dash by U1 dash equal to minus V2 dash by V1 dash. Okay, you make it a point that, so if I take positive, U2 dash by U1 dash equal to V2 dash by V1. The ratio of velocities before collision is equal to the two bodies, ratio of first body, second body to the ratio of the first body before collision equal to after collision about the center of mass frame of reference. Okay, now let me consider this. We know that u1 dash equal to u1 minus vcm, right? This already I have done for you. So u1 minus, what happens ma? m1 u1 by m1 plus m2, right? Because u2 is 0. u2 is 0, m1 u1 by m1 plus m2. Similarly, I'll have, so what happens, I'll solve this equation. So u1 dash equal to m1 u1 plus m2 u1 minus m1 u1. So m1 u1, m1 u1 gets cancelled. I'll get m2 u1 by m1 plus m2 by m1 plus m2. This is u1 dash. Okay. Now, what is v2 dash? Equal to minus VCM. V2 dash equal to minus VCM. That is equal to M1 U1 by M1 plus M2. Simple. M1 U1 by M plus M2 because U2 is 0. Okay. So M1 plus M2. So by we know that it's an elastic collision. We have conservation of kinetic energy. So half M1 U1 square plus half M2 U2 dash square equal to half M1 V1 dash square plus half M2 V2 dash square. This is conservation of kinetic energy. So I'll cancel half, 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 half. So I'll get, what I'll get? I'll get on both sides m1 u1 dash square plus m2 u2 dash square equal to m1 v1 dash square plus m2 v2 dash square. Okay, so I'll get m1 u1 dash square plus m2 u2 dash square equal to m1 v1 dash square plus m2 v2 dash square. Okay, now substituting u2 dash and v2 dash from the two previous equations which I have written here. What are those now? u1 dash equal to m2 u1 by m1 plus m2. What is v1 2 dash? What did I get? What did I get? You tell me. v2 dash is minus m1 u1 by m1 plus m2. Okay, now I substitute the two equations here by using v2 dash u2 dash and v2 dash in this equation. What I'll get here? You tell me. m1 u1 dash square plus m2 into m1 by m2 u1 dash square equal to m1 v1 dash square plus m2 into m1 by m2 square into v1 dash square. Okay, now what I'll get here? Now solving these equations here, m2 square gets cancelled, m2 square gets cancelled. Now finally I'll remain with m1 u1 dash square plus m1 square by m2 square u1 dash square. Okay, students, m1 square by m2 square into u1 dash square, m1 square by m2, because here only one m2 gets cancelled, here 2 remains, 1 remains. m1 v1 square dash square plus, here one m2 and this m2 gets cancelled, no? So m1 square by m2 v1 dash square. Okay, so I'll write here, I'll take this common, m1 u1 dash square, let us take common from here and here. What I'll get? 1 plus m1 by m2 equal to, I'll take m1 v1 dash square. What I'll get? 1 plus m1 by m2. So both sides m1 plus m1 by m2 and 1 plus m1 by m2 gets cancelled, right? So I'll get u1 dash square equal to v1 dash square. Here m1 also gets cancelled. So finally I'll get u1 dash square equal to v1 dash square, implies u1 dash equal to v1 dash, right? So what I'll get from this? u2 dash equal to minus v2 dash, right? So u1 dash equal to v1 dash means u2 dash equal to minus v2 dash. It's in the opposite direction. Hence, in the center of mass frame, what we can say, the magnitudes of velocity of the particles remains constant, that is u2 equal to v2, but the direction will be changed, that is minus v2 dash. v2 dash is equal to minus v2 dash. Okay, students, so finally we have calculated the final velocities v1 dash and v2 dash in terms of u1 dash and u2 dash by using law of conservation of energy and law of conservation of momentum. Okay, law of conservation of energy and law of conservation of momentum, because it is an elastic collision. Okay, because it is an elastic collision. Okay, students, so let me come back to your PPT. See, finally, we have done today work energy theorem. What does it mean? The work done by a force on a particle, because of a force on acting on a particle, is always equal to the change in kinetic energy. Change in kinetic energy of the particle. So this is nothing but work energy theorem. So now we have understood what is elastic collision and what is inelastic collisions. Okay, based on the conservation of energy and momentum, we can say that in elastic collision, both energy and momentum are conserved, but in inelastic, like atomic and nuclear reactions, comes under elastic collisions. When in elastic collision, we have only kinetic energy is not conserved, but momentum is conserved. Next, we have elastic collision in 2 dimensions. We have solved and we have found out the expressions for v1 dash and v2 dash. Okay, so next So this is the end of your session, students. So next time we'll see with we'll come back with different topics. Okay. Thank you, students. Thank you so much.